The next speaker is Alexander Betts, currently at Harvard, but soon to be at Cornell, and he will talk about unexpected algebraic points in non-abelian Chabauty loci.
Thank you very much, Jan. So I guess as the first of Mignon's former students to be speaking here, it would normally sort of fall upon me to begin my talk with like some amusing, like whimsical anecdote of our time in Oxford together. And I was sort of thinking about what I wanted to say before I start with the maths. And in the end, I decided, rather than sort of talk about a specific anecdote of our time together in Oxford, I wanted to just like, when I was thinking back, the one thing that really struck me about all my interactions with Mignon is like his constant like warmth and empathy as a person. And I sort of want to just say a little bit about this. I'm sure I'm going to be embarrassing Mignon at this point. I'm sorry.
You have nothing mathematical to contribute. You have to be one.
And his wisdom. But yeah, so I started my PhD with Mignon in 2014, and I graduated in 2018. But since then, while I've been learning life as a postdoc, I've kept in pretty much constant contact with him, and through certainly in the last few years, while I've been dealing with all the stress of job applications and the trying to sort out a two-body problem, which I'm sure there are many people in this room who know that this is a very stressful time and a time which really eats into your self-confidence and your self-belief. And somehow whenever I would talk to Mignon, he would always say know the right things to say, and know those times when I was finding it hard to believe in myself as a mathematician, he would be there to because he believes in me, and this was be able to hear this was really important for me at those times when I was feeling quite low. And so I really think that without Mignon's support, this would have been so much harder to get through to the stage where I am, where I've now actually resolved my problem. And so I just wanted to begin with a very personal thank you to Mignon for all the support you've given me over the years. With that said, I'll now switch into math mode for the remainder of my talk. So what I'm going to be telling you today is going to be sort of a rather sketchy, big picture way of thinking about some topics in quadratic Chabauty. So there's going to be more towards a large overview than specific detailed mathematics in many places. But at the end, I'm going to touch on some joint work with Jen we've been exploring over the last year or so. If you want to follow along in your own time, I've put some slides available on my website, so you can follow those if you want. And I guess finally, with regards to the title of this conference, I guess my talk will be about arithmetic and geometry, and it will be happening in this space, and it will be taking up about an hour of your time. So roughly speaking, what I'm trying to about today is just a new way of thinking about what is done in quadratic Chabauty, and in particular talking about this in a way which emphasizes algebraic structures as opposed to the sort of p-adic analytic structures with Coleman integrals, which we heard about a lot in Kieran's talk. And in the cases where I can actually do this change in perspective, one of the advantages here is we will see connections with the theory of unlikely intersections begin to become rather clearer than they maybe are from the original setup. So this is the main thing I want to achieve today. But I'm going to begin just with a little bit of motivation, why I've been thinking about this. This is, for me, coming from thinking about Mignon's conjecture about the effectiveness of non-abelian Chabauty. So my general setup for my talk, I'm going to be having throughout a smooth hyperbolic curve over the rational numbers with a fixed base point. And I'm going to let myself be a bit vague about whether or not my curve is proper or not at various different stages. Sometimes it will be proper, sometimes I will be non-proper, and I've chosen a model, but hopefully it shouldn't be too confusing. And then whenever you see the letters G, R, or rho appear, they're going to have specific meanings. So G is the genus of my curve, R is the Mordell-Weil rank of the Jacobian, and rho is the rational Picard number of the Jacobian. These are quantities we're used to seeing in abelian and quadratic Chabauty. And then the general setup of what non-abelian Chabauty does in some general context is you take some, choose some quotient of the p-adic étale fundamental group, and associated to this, you get a certain subset of the p-adic points containing the rational points. And not going to spell immediately how this is actually constructed, but I think it is quite useful to think of this as really some kind of like obstruction theory, where you're defining some obstruction to a p-adic point being rational, and so you'll be trying to learn something about where the rational points lie inside the p-adic points. This is a perspective that Mignon told me about many years ago. And although there will be a couple of times where I'm going to talk about a general quotient of the fundamental group U, for most of the talk, we're only really going to be interested in two different quotients. First one is the abelianization of the fundamental group. And I see that my editor has Americanized my spelling. I think it's correct later in the talk. So this quotient U1 is the abelianization of the fundamental group, and so this gives you some subset of the p-adic points containing the rational points, which is XQP1, which you've already seen in Kieran's talk. This is the Chabauty-Coleman locus, and the other one we're going to see is the quotient which appears in quadratic Chabauty, and this is now suffice it to say that this will be some extension of the abelianization by ρ-1 copies of QP1 as a Galois representation. So then we get corresponding quadratic Chabauty subset of the p-adic points, which I'm going to denote by this sub QC. So, if we switch back to thinking about a general quotient U, as you vary your quotient, you get different obstruction loci inside the p-adic points, and as U gets larger and larger, these get smaller and smaller in at least a weak sense. And so, as Kieran mentioned, Mignon formulated a conjecture in his talk at the IHS in 2012. This was then made more precise in a paper with Jen Balakrishnan, Ishai Dan Cohen, and Stefan Wevers. But the idea is that if I take a large enough quotient of my fundamental group, then I should in fact exactly cut out the rational points. And so without dwelling too much on why I believe this to be true, one can certainly ask, well, where would I expect this to start holding? So for which quotients U should I expect that this locus is equal to the set of rational points? And there's a reasonable way you can think about this. So these loci, these are always like the common vanishing locus of some number of Coleman analytic functions. This is, as Kieran mentioned, and somehow the shape of this locus depends a lot on the number of functions which cuts it out. So it can certainly happen if you choose a really small quotient of your fundamental group. You might be unlucky and you get 0 functions cutting out this locus. So then it is just all the set of p-adic points. And so you've learned nothing at all about the set of rational points. But as soon as you get at least one non-zero Coleman function out of this method, then this locus that you get is a finite set because of some isolation of zeros principle. And so at this point, we are much closer to actually knowing the rational points. But as Kieran mentioned, you can often, this set will often contain like other irrational points. I mean, typically just some random transcendental points. We have no idea why they're there. They're just there because they are extra incidental zeros of an analytic function. But if we have at least 2 functions cutting out this locus, then we expect to be in a much better situation, because in this case, our XQP is like something one-dimensional, and we're looking at the common vanishing locus of at least 2 functions, and we would expect generically that they don't have any zeros at all. So somehow, the only common zeros of these functions should somehow be there for a reason, like because they are rational. And so we maybe expect that in this final case, where this locus is sort of overdetermined, we expect to be in a kind of much better position than in any of the previous cases. So you might naively guess that in this final case, where we have 2 different functions defining this locus, that it should actually be equal to the set of rational points. After all, if you have some other random transcendental point, why on earth should it be in this locus? There's no good reason why to expect it to be there. And perhaps the fact I've called this a naive guess is going to betray what's going to happen on the next couple of slides. But it turns out that this is not true. So I'm going to give you several different examples, beginning in the setting of abelian Chabauty. So in the setting of abelian Chabauty, the number of functions that you get is basically equal to the genus minus the rank. So for example, one of the first interesting cases when you have a genus 3 curve whose model such that the Jacobian has model rank 1. And this was studied computationally by Jen Balakrishnan, Francesca Bianchi, Mirella Cipriani, Victoria Cantarell-Farfan, and Anastasia Etropolsky. And they studied a wide variety of hyperelliptic genus 3 curves with rank 1. And they found, for example, this curve here. So then if you look at the 7-adic abelian Chabauty locus for this curve, they computed it explicitly. And what do they find? Well, they found that the 5 rational points on this curve, which of course have to be in there, but they found actually extra points. So they found as well, they found 3 Weierstrass points. So on the Weierstrass points on this curve, there are 7 Weierstrass points. 3 of them are Q7 rational, and those 3 points showed up in this locus. And they found even extra points which are not even Weierstrass points, namely the 2 points with x coordinate 0. So you can already see in this example, which there are like a couple hundred examples, I think, in their paper. We can already see that this naive guess for when Kim's conjecture should hold is not entirely accurate. There was a similar paper a couple of years later by Sachi Hashimoto and Travis Morrison, who did the same thing, but for Picard curves of genus 3 and rank 1. And they found this example as well, where if you compute its 11-adic abelian Chabauty locus, you get the set of rational points, which is just a single point at infinity here. But you also get this other rather mysterious point involving a cube root of 13/16.
So what happens if you use other primes?
So I don't remember exactly off the top of my head for these particular curves, but if you choose, obviously Q11 contains a cube root of 13/16. If you choose another, what will typically happen is if you choose another prime, then you'll still have the point at infinity. But if 13/16 is not a cube in QP, then that point will disappear. That's sort of generically what seems to happen here.
But if it is, then it will appear.
Yes, this is this will become apparent later on, but yes. Yes, these sorts of examples have been found not just for like abelian Chabauty, but also genuinely for non-abelian Chabauty. So it was also studied by Francesca Bianchi, who was interested in quadratic Chabauty for integer points on once punctured elliptic curves. And if you do this for a rank 0 elliptic curve, you're again in the situation where your quadratic Chabauty locus is cut out by 2 independent functions. But again, it can contain non-rational, really non-integral points. So in this example, this particular elliptic curve, it has rank 0, and the 5-adic quadratic Chabauty locus that contains the integer points, of which there are in fact none on this curve. But it actually also contains 2 extra points, the points with x coordinate 5. And the final example I'm going to mention, which is of maybe a rather different kind to the others and sort of less what I'm going to be talking about today. But there are examples where you can have these loci cut out by arbitrarily many functions and still have points that you didn't expect to lie in there. So this is an example due to David Corwin and Ishai Dan Cohen. So if you're looking at the thrice punctured line over Z with an odd prime inverted, so this is like an S integral points problem, then you can look at this the non-abelian Chabauty locus for what's called the depth n polylogarithmic quotient. And as you increase n, this can be cut out by arbitrarily many functions. And it turns out that these loci always contain -1. And even though -1 is not actually an S integral point on this curve, it's a rational point, but not an S integral one. So this in some cases indicates that you can get examples of this phenomenon where your locus is cut out by 3, 4, 5, or as many functions as you want. So if our guess was too naive initially, it's at least these examples indicate that there may be some structure going on, because if we look at this example for Francesca's, okay, we have these extra points show up in this locus, but they aren't like random transcendental points. They're in fact points defined over Q adjoint I. So they're actually algebraic over the rational numbers. And similarly, in this example of Sacchi and Travis, again, we have something which is defined over the number field formed by adjoining a cube root of 13 over 2. And back in this very first example, all these extra points we had were either defined over Q adjoining a square root of 2, or they were these Weierstrass points where your y coordinate is 0 and your x coordinate is a root of this degree 7 polynomial. They're all algebraic. Kieran.
Might be a good point to ask. Does that persist for all of their examples?
The Weierstrass points being in there?
No, the fact that you can identify all of everything as an algebraic point.
In every single one of their examples, it's always algebraic, yes.
Extraneous points that remain after you have two Kim functions.
Yes, exactly. So yes, so it's maybe reasonable to expect that this should be the generic behavior, is that in this kind of nice situation where we have two functions, then these loci they might not be just the rational points, but they should contain only algebraic points. And this is something which was already conjectured for abelian Chabauty by Michael Stoll. It is in like a preprint version of a published paper that I don't think the conjectures appears in the final version. I'm very slightly paraphrasing what he says here, but Michael formulates this actually rather stronger conjecture. That if I have a smooth projective curve with the genus minus the rank being at least 2, this then means that my abelian Chabauty locus is cut out by at least 2 functions. Then Stoll conjectures that there should be some finite subscheme of my curve defined over Q such that this abelian Chabauty locus is contained inside Z, but almost all prime. And I sort of think of this conjecture as really combining 2 different themes, one of which we've already spoken about, because this subscheme is defined over Q, it tells you that this abelian Chabauty locus should only contain algebraic points, as we've seen on the next few slides. But actually, I think there's something quite remarkable postulated in this conjecture, namely that this subscheme Z is independent of the prime P. So it also postulates like an independence of P result for these abelian Chabauty loci. And so one particular consequence of this conjecture would be that the size of the abelian Chabauty locus is bounded uniformly as you vary P, at least for almost all P. Akira?
So I suppose this also implies that there is a set of primes of positive density where you get exactly the QP points, basically.
Yes. So I've
Like Shabatarov.
yes. I think,
Or is it possible that I guess in principle it could happen that there's no you could have some weird thing where you have enough algebraic points over different fields that there's no way to sort of make them all disappear simultaneously.
oh, you're asking about whether you can choose a P to.
Yeah, whether there exists a P or, positive density set of P where you actually get these things. I guess it doesn't formally follow now that I say it.
Yes, and one thing that at least in all the examples I'm going to be talking about today seems to be the case is seems that you can choose Z so that this is actually an equality and this is for like all good reduction primes. So something even stronger might be true. Okay, but it's hopefully clear that there should be some generalization of this conjecture to non-abelian Chabauty, and so this was like in Francesca's work on one-function elliptic curves. She at least she alludes to how to generalize this conjecture, but I sort of want to try and pin it down somewhat precisely here, because this is sort of something I'm interested in understanding better. So yeah, so let's suppose that we've picked our quotient of the fundamental group, and I'm going to say it's of motivic origin in some sense, and this is going to be a quotient such that the corresponding Chabauty Kim locus is cut out by at least 2 functions. I'm going to be deliberately vague about what I mean by of motivic origin. Hopefully, this is something which I feel should be clear if you have a quotient, whether it's of motivic origin or not. But one particular consequence of being of motivic origin should be that not only do you have this quotient of the p-adic fundamental group, you should have like corresponding quotients of the q-adic fundamental groups for all other primes q. And so then what I would conjecture here is that there should be, in this setup, there should be a finite subscheme of your curve defined over Q such that the q-adic non-abelian Chabauty locus for this quotient is contained in Z for almost all primes Q. This may be a very optimistic conjecture, but this is probably I think it's the natural thing to believe in this situation. So before I crack on and say anything about this conjecture, does anyone have any questions they'd like to ask about this motivation or thing? Yeah. Okay, so what's going to take up my time for most of the rest of the talk is really trying to explain somehow the easy cases of this conjecture. I'm definitely not going to be attempting to do much actual hard mathematics here. But hopefully oh yes, Anna.
Didn't define what is motivic, but is it natural to expect this Z to be defined over Q?
I guess it's defined over Q. If I had like some points defined over a number field, like I could take the Galois orbit of all of those points, and then that would be the points of a subscheme defined over Q. Yes. Yeah. Yes. The more way that defined over Q doesn't mean that all of its points are rational. This means that they're algebraic. Yes, and so hopefully I'll also make it clear where one might see unlikely intersections begin to appear in this story. And I'm going to begin with talking about abelian Chabauty, i.e. non-abelian Chabauty for the quotient U1. I'm going to be definitely talking about this in like a completely ahistorical perspective, like the sort of going backwards in time in some sense. So yeah, so this is all about this abelianization of this fundamental group. And the way that it's most useful to think about this abelianization in the context of abelian Chabauty, especially as a special case of non-abelian, is that this quotient is nothing other than just the fundamental group of the Jacobian. So rather than talking about it as the abelianization of the fundamental group of X, let's just call it the fundamental group of J. And so what Kieran's already described in his talk is that you can actually describe this this abelian Chabauty locus purely in terms of the Jacobian, not in terms of any fundamental groups. This is, of course, how it was originally done. And so here's like how I like to think about this. So we've got the rational points on the curve is the thing we want to understand, and these are obviously a subset of the p-adic points, which we want to understand this inclusion on the left-hand side here. And so obviously X embeds via the arbor Jacobi embedding inside its Jacobian. So we sort of have this left-hand square here. And now, the one thing we know about the Jacobian is it's an abelian group. And so for abelian groups, we can do all sorts of things like tensor them with Q or tensor them with QP or all the sorts of constructions. And so on the right-hand side, what I'm going to do is tack on a second square where I'm like tensoring the groups of either rational or QP points on the Jacobian and tensoring them up with QP. So this tensor product symbol is either like a normal tensor product or some kind of topological tensor product as needs be. But anyway, just using the group structure on the Jacobian, we can describe a nice big rectangle like this. And by for consistency with the general non-abelian Chabauty setup, I'll call this right-hand vertical map loc P, the localization map. I'm going to call this composition along the bottom JP1 for the that's a sort of non-abelian, that's the abelian map for my curve. And then the fact here, which is really a question of translation definitions, is that this abelian Chabauty locus is nothing other than, well, you start in the top right-hand corner. You cannot stand there. Okay. You take the image of the top right in the bottom right, and you take the pre-image of that in the bottom left. This, I hope it's clear from this that this at least is a subset of the p-adic points and contains the rational points. So one thing that we can learn immediately from this diagram is what goes on when when R is 0, so when the Jacobian has rank 0. Because in that case, the top right-hand guy, this is the rational points tensor with QP, rational points is finite. The top right becomes like a single point. And then in that case, this definition is just saying that XQP1 is just the kernel of this bottom. And the kernel of this composition has a special name. It's the torsion packet containing the base point. Because the fibers of this right-hand map here, these are just the translates of the torsion in J. And what I'm doing is I'm basically taking a translate of the torsion, well, taking actually just the torsion in A in J and intersecting it with the curve X. So this is a torsion packet. And this is the sort of thing which is studied a lot in the sort of classical unlikely intersections literature. So in particular, we have the Minian-Mumford conjecture, proved by first by Reynaud, and then later by Pilar and Zania using more complex analytic methods. And the consequence of the statement basically of the Minian-Mumford conjecture is that all of these torsion packets on my higher genus curve are always finite. And so I think what I get by combining these two perspectives.
So is a torsion packet just the difference between two rational points? 2 points on the curve?
Yeah, so I guess a torsion packet is an intersection between my curve and a translate of the torsion on the Jacobian. So this will be a subset of the curve consisting of all points whose difference is a torsion point on the Jacobian. Yeah. So if I combine these thoughts, well, there's abelian Chabauty in this rank 0 case. The abelian Chabauty locus is a torsion packet, and that torsion packet is finite. And it's finite as a subscheme of X. And so the consequence of all this is that we've actually, Stoll's conjecture actually holds for when the modular rank of the Jacobian is 0. This is kind of the easy case of Stoll's conjecture. And yeah, as I said, rather than talking about anything hard, I'm going to talk instead about the easy case of the non-abelian Stoll's conjecture. So we're going to do this all in the setting of quadratic Chabauty. So let's try and build a parallel theory for quadratic Chabauty. As I mentioned at the beginning, quadratic Chabauty is non-abelian Chabauty where my quotient is some extension of the abelianization by rho minus 1 copies of QP1. And even though this determines the quotient uniquely, but it's still very useful to ask which quotient of the fundamental group actually is this? And there's a very nice answer, which is basically given by Edixhoven and Lido, which is, well, it's sort of a very geometric thing. So if I look on the Jacobian, there's a natural way to construct a torsor under GM to the rho minus 1 over the Jacobian, which trivializes when I restrict it to my curve. You can sort of do this by just thinking about the orders of the various Néron-Severi groups, and thinking about the Poincare bundle, Poincare torsor. And so if I think about this, well, I think about this is like, so X embeds inside its Jacobian via the arbor Jacobi embedding. I have this torsor over the Jacobian, and the fact that it trivializes when I restrict to X means that the arbor Jacobi embedding of X lifts to an embedding of X inside P. So I have this other nice large variety containing my curve as a closed subscheme. And then the significance of this quadratic Chabauty is really that this quotient, this UQC, this is nothing other than the fundamental group of P. So if I'm going to be very, very precise here, the map from X to P that I've just constructed, that induces a map on fundamental groups, and that is the quotient map from the fundamental group of X to UQC.
It doesn't depend on the choice of a Néron-Severi class that pulls back to, that becomes trivial in X?
I think you can do this in a way which is, you choose a basis of the kernel of the map on Néron-Severi groups, And that gives you a,
Into the row minus one.
yeah, exactly, yeah.
Oh,
You can do this for individual ones one at a time. So thinking back to what we did for abelian Chabauty, what we'd like to do is to describe the quadratic Chabauty locus purely in terms of this torsor P, rather than actually in terms of the quotient. So this is going to be very obviously inspired by the work on geometric quadratic Chabauty, or I guess the formulation of geometric quadratic Chabauty by Edixhoven and Lido, who were really thinking about these torsors and trying to understand how to use them to give an obstruction to rational points. And just in very, very broad strokes, what their method does is it defines some other obstruction locus, the geometric quadratic Chabauty locus. And again, it's a subset of the p-adic points containing the rational points. And this is not actually literally the same as quadratic Chabauty. It gives you actually an obstruction which is at least as strong as quadratic Chabauty and can actually sometimes be stronger. So sometimes the geometric quadratic Chabauty locus will be a proper subset of the quadratic Chabauty locus. Examples found by Juanito Duque-Rosero, Sachi Hashimoto, and Pim Spillier. So really what I'm wanting to do is do something very similar to what Edixhoven and Lido did, but describe an obstruction in terms of P, which recovers exactly the quadratic Chabauty locus, not this finite locus. And if we think back to what happened in the abelian case, a very, very important role was played by the fact that the Jacobian is a group, as an abelian group. And unfortunately, these torsors P, these don't have a group structure in general, not even a non-abelian one. Nonetheless, there is some structure available which we want to leverage. This is given by the rather beautiful theory of cubical structures developed by Larry Breen. So if you've seen bi-extensions before, cubical structures are like a cousin to bi-extensions. And I'm not going to give you a careful definition here, but very roughly speaking, what we're thinking about is we're thinking about torsors under abelian groups over other abelian groups, like a torsor under GM over an abelian variety. And if I have such a thing, there's an interesting G torsor over A cubed that I can produce. Namely, I can think about maps from A cubed to A, where I add together some of the coordinates, like maybe the map x, y, z goes to x plus z. And if I pull back my torsor along any of these addition maps, this gives me a G torsor on A cubed. So I obtain in this way 8 different G torsors on A cubed. And I can just take like a suitably alternating tensor product of all of these torsors. This gives me what I'll call θ3. It's the theta torsor associated to the torsor P. This is a G torsor on A cubed. And then, according to Breen's definitions, a cubical structure on this torsor is a trivialization of the theta torsor, which satisfies certain conditions which kind of look like unitality, commutativity, and associativity. And yes, and I'll call, if I have a torsor with a cubical structure, I'll call it a cubical torsor. And the idea I kind of want to promote here is that you can treat these sorts of cubical torsors in many of the similar ways you can actually treat abelian groups. So I guess before I say that, I'll give you 2 examples. The archetypal example of a cubical torsor is if you take any torsor under a torus over an abelian variety, there's a unique cubical structure coming from the theorem. So if you think about the case of the torus being GM, then I'm just really talking about line bundles, and this is like the usual theorem of the cube. But there are also more like down-to-earth hands-on examples. So if you just take an extension of one abelian group by another, you can use the group law on that extension to define a cubical structure on the middle group. And it makes it sort of into a torsor under the kernel over the quotient. And so in some sense, whatever cubical torsors are, they are some generalization of extensions of abelian groups. In fact, they're even a generalization of central extensions of abelian groups if you write your terms in the suitable order. So these sort of more concrete examples of cubical torsors, and they inspire us to try and develop analogs of things we can do for abelian groups in the setting of cubical torsors. And the main one that relevant for us is, well, if I have an abelian group, I can tensor it with QP to get some kind of QP vector space. It turns out there's an analogous construction for cubical torsors. So I've given this some name. I'm definitely still workshopping what this name is actually going to be in the end. But basically, if I take a cubical torsor, there's a natural way of producing something called Q tensor P, which is it's again a cubical torsor, but it's a torsor under Q. So if P was a torsor under G over A, then this Q tensor P ends up being a torsor under Q tensor G over Q tensor A. And if you like, you can construct this explicitly. You can also characterize this by a universal property that looks exactly like the universal property for the tensor products. So we have these sort of algebraic constructions that are still available in the world of cubical torsors. And there's a similar like topological one for if I have a topological cubical torsor, I can again define a topological tensor product with QP. So I'm going to use these operations to actually describe Chabauty for you now. So I'm going to simplify my life before I actually get started, by assuming that X has everywhere potentially good reduction. This will just make the exposition cleaner. And now this torsor that I'm looking at, I'm going to need to be careful not to talk about its rational points, but instead about its integral points. Or more precisely, you can show that this torsor, which is like it's a variety of a Q, you can show that it has a Néron model, and this P comes with there's a base point on P, and so you can talk about the component of the Néron model containing the base point. We'll call that P naught, and whatever this thing is, it ends up being a cubical torsor under GM to the rho minus 1 over the identity component of the Néron model of the Jacobian. And so now we can give a new description of Chabauty. So again, we're going to start off with the rational points on X embedded inside the QP points. And now, as I said, we can embed X inside P. And it turns out that this embeds the rational points of X inside the integral points on this P naught, and similarly on the p-adic side. So we've sort of got the left-hand side here by some kind of functoriality argument. And now everything in this middle column has is a cubical torsor. So I'm allowed to tensor it with QP in possibly some topological sense. And that gives me this right-hand square here. And so again, I'm going to call this right-hand vertical map localization and this bottom map JP2 for like a non-abelian Kummer map. And then the theorem is that this diagram here really recovers quadratic Chabauty. That is to say, the quadratic Chabauty locus is actually equal to the image of this map pulled back under JP2. So probably the most technical thing I'm going to say is I just want to give some idea for experts, maybe like how you would prove such a thing. And so somehow the idea is not just that this construction recovers the quadratic Chabauty locus, but actually the outer part of this rectangle just is the usual commuting square you get with Selmer varieties of non-abelian Kummer maps in the setting of quadratic Chabauty.
Maybe that's a difficult question, but could you say maybe in a word what the geometric quadratic Chabauty set would be in this language?
Yes. In this setting, geometric quadratic Chabauty is you take the closure of the image of the middle map and then put it back to here. Yes. At least if you choose you might have to take a tensor power of P at some point. Okay, so I wanted to at least indicate why this outer square is actually the usual diagram with Selmer schemes. I'll just give you one small part of this, which is we have this local Selmer scheme associated with the quotient UQC. That is this thing here. And I'm going to claim that this is actually isomorphic to the ZP points on P naught tensored up with QP. And when you set up the theory appropriately, this is actually not too difficult to prove. So first of all, one of the things that we know about this local Selmer scheme in this setup, it has a torsor structure in a natural way, and just coming from the where you define it. And then you can actually show because of this that the cubical structure on P0 induces a cubical structure on the local Selmer scheme. This is because UQC is just the fundamental group of P. So the structure on P induces a structure on its fundamental group, induces a structure on the local Selmer scheme. And this cubical structure is such that the Cohen map, the non-abelian Cohen map from ZP points on P0 to this local Selmer scheme, this is actually a morphism of cubical torsors. And so via some universal property, we'll factor through sort of the QP linearization. So we at least have a map between these two things I claim are isomorphic. And then by some kind of 5-lemma style argument, to show that this top map is an isomorphism, I just need to show that the corresponding maps for the Jacobian GM are both isomorphisms. And they are, at least if you sweep some minor Tate-Sheff-Ravitch issues under the rug.
Can you also follow up on Jan's question? So
Yes.
the diagram you had on the previous page, does that also explain the difference between the geometric QC locus and the QC locus? You said sometimes they're different. You can see that in this diagram.
It should exactly. It should like certainly explain why geometric quadratic Chabauty is contained inside quadratic Chabauty. So yes, in the end, the conclusion is that I guess the conclusion is that this guy is your local Selmer scheme. So it's the right object sitting in the right part of the square to identify this with non-abelian Chabauty. And anyway, so
Oh, sorry, could I ask one question about the next slide that you had a moment? A very stupid question, but where is the cubical structure being used in this argument?
the fact that this map here is a morphism of cubical structures means you get an induced map on the out of the QP
Oh, I see, yeah.
QP rationalization, yes. If you drop the word cubicle, you can't actually make sense of rationalization of a torso. Okay. Anyway, sort of with all these technicalities aside, once you're happy that this actually is recovering quadratic Chabauty, we can now play exactly the same game and try and recover some easy cases of Stoll's non-abelian Stoll. So what happens if I take if my Jacobian has rank 0, then it's P0 of Z. This is a torsor under a finite group over a finite group. So when I tensor with QP, that just becomes a single point. And so then this quadratic Chabauty locus ends up being just the kernel of this bottom composition, just as before. And the fibers of this composition along the bottom, these don't have a pre-existing name, but I'm going to call them the higher torsion packets on X. These are in some sense like the intersection of X and certain structured subsets of P0. And then and so what we would again hope to be the case is that all of these higher torsion packets should be finite. And this would be like some version of the mini-Mumford conjecture for these for P instead of for abelian varieties. And it turns out you can prove this. There are two different ways of getting at this, but you can actually kind of carry out the analog of this P-lasagna strategy, this complex analytic approach. You can actually still carry through in this context and prove that all of these higher torsion packets are finite. So in the end, we get the same conclusion as before. If the model V rank is 0, then the quadratic Chabauty locus is a single higher torsion packet, and that is a finite subscheme of my curve. So I've proved non-abelian Stoll's conjecture for the quadratic Chabauty locus when the Jacobian has rank 0. And now, so this is, I think, the easy case of non-abelian Stoll's conjecture. It still requires quite a lot of theory to be set up in order to be able to access this. And I guess the thing I should own up to here is that in terms of this final result, at least, this is only really interesting in the case that X has genus 1. So when I'm talking about once punctured elliptic curves, because for curves of higher genus, this non-abelian Stoll's conjecture actually follows from abelian Stoll's conjecture in the rank 0. But nonetheless, actually, it turns out that quite a lot goes on for once punctured elliptic curves. We've already seen that example that Francesca Bianchi found. And this is something, this particular case is something that Jen and I have been thinking about a lot over the last 2 years or so, of really trying to understand these quadratic Chabauty loci for integral points on rank 0 once punctured elliptic curves. And in particular, understanding these sort of unexpected algebraic, non-rational algebraic points that appear. So yeah, so from now on, we're going to assume we're talking about once punctured elliptic curve of rank 0. And what I described previously tells us that there's a finite subscheme of this curve such that, in fact, the quadratic Chabauty locus is equal to the ZP points on this subscheme Z for all primes of good reduction. So this Z is defined over Q. And so, what we would like to do is understand what on earth can this Z look like? What kinds of irrational algebraic points might we see in this locus? Because the dimension heuristic predicts they shouldn't exist, we'll call these unexpected points that appear. These are also sometimes called mock rational points. And the point is that, we can actually say a lot about them. So first of all, in Francesca's work, she showed that all of these unexpected points are actually always torsion points on my elliptic curve. Because one of the analytic functions defining the quadratic Chabauty locus is the elliptic logarithm, whose kernel consists of just the torsion points. But because we have now this algebraic way of thinking about the quadratic Chabauty locus, it gives us another way of describing this, which doesn't involve any p-adic functions at all, and just involves kind of much more classical things like division polynomials, invariant differentials, and so on. And is also a description which doesn't depend on p in any way. And so when you use this, you can actually then start to try and analyze what sorts of points can appear. And so the result that we have been working towards, we've run now, our computations have finished up to order 50, is that suppose that I have one of these once punctured elliptic curves of rank 0, and if I've got some unexpected point, the torsion point, so it has some order. And what I can tell you is that at least when the order is at most 50, then the order has to be one of these 10 listed values, or 11. So it's either the ones you might expect naively, like a 2, 3, 4, 5, 6, 7, 8, 9, 10, and 12. So the ones from Mazur's theorem, but also 15. I definitely don't have any time to tell you exactly how the proof goes. In very, very broad terms, the idea is, because we have this algebraic description of the quadratic Chabauty locus, we can write down a condition on the J invariant of your elliptic curve in order for it to have, or at least a necessary condition on the J invariant, in order for it to have an unexpected point of some fixed order n, and then you can just solve for those J's, and then you've sort of determined all the possible J invariants of elliptic curves with unexpected points of a particular order. And I think I'll at least finish by saying that for every n on this list, we have at least one example which realizes that order. And so I'll finish with the final example for my talk, which is, so let's take the once punctured elliptic curve with this Weierstrass equation. This is again a rank 0 elliptic curve. So the quadratic Chabauty locus is cut out by two functions. If you compute the quadratic Chabauty locus, you will find it contains not just the integral points, I can't remember what they are in this case, but it also contains 5 points of order 15, namely the points with this x coordinate. And if, as sort of related to Dick's question from earlier, you'll see these points appear whenever those points are QP rational. So whenever QP contains a square root of 5 and whatever other random algebraic numbers crop up here. And at least make an observation that even to state this example, you can verify this computationally if you like, but you can only verify it computationally up to an arbitrary high precision. So the assertion that your quadratic Chabauty functions vanish at this actual point is not something you can officially completely verify computationally. And so we already, even to exhibit this example, we need all of that algebraic theory set up on in the previous part of the talk. But with hopefully that little taster of what we can really sort of say using these ideas, I think I'll finish here and take any questions.